Hello students, welcome to 6th lecture of D and F block elements. In today's lecture, we are going to discuss about some important compounds of D blocks. So mainly we are going to discuss about oxides and oxoanions of transition elements in this topic. These oxides are generally formed by the reaction of metals with oxygen at high temperatures. All the metals except scandium form MO oxide which are ionic. The highest oxidation number in the oxides coincides with the group number and is attained in scandium O3 to Mn2O7. Beyond group 7, no higher oxides of iron above Fe2O3 are known. Besides the oxide, oxocations stabilizes V5 as VO2 plus and V4 as VO2 2 plus and titanium 4 as TiO2 plus. As the oxidation number of metal increases, ionic character decreases. In the case of MnO2O7 is covalent green oil. Even CrO3 and V2O5 have low melting points. In these higher oxides, the acidic character is predominant. Now, reason for this is when oxidation number of metal increases, stronger nuclear power will be more dominant, and because of that, metal ions also attracts electrons strongly. So simple illustration will be, suppose we have a metal with a +1 charge and oxygen having -2 charge. So obviously, as we know, oxygen attracts electrons strongly. And in oxide formation, if bond is ionic, then oxygen will be in -2 oxidation state. Now in this case, let's say our metal contains 25 protons at the center and now it has 24 electrons. So that's why it is +1 in charge. So right now 25 protons are attracting 24 electrons. So attraction will be comparatively moderated. Now let's say our metal exhibits +7 oxidation state. That means still we have total 25 protons in the nucleus, but number of electrons will be 18. That means 25 protons are attracting 18 electrons, and that's why attraction will be comparatively very strong. So because of effective nuclear charge, metal also attracts electron strongly. So that's why both of the elements or species present in the oxide are trying to attract electrons strongly, and electronegativity difference decreases. And because of that, at higher oxidation state, compound becomes covalent. That means it has more than 50% covalent nature. Whereas in first case, our metal atom was was in +1 oxidation state, and we have oxygen, which is comparatively very strong electronegative element, and we have comparatively large electronegativity difference, and that's why it has more than 50% ionic character, and overall it is ionic compound. In this case, it has more than 50% covalent character. Thus, Mn2O7 gives HMnO4 and CrO3 gives H2CrO4 and H2Cr2O7. V2O5 is, however, amphoteric through mainly acidic, and it gives VO4 3- as well as VO2 plus salts. In vanadium, there is gradual change from the basic V2O3 to less basic V2O4 to amphoteric V2O5. Now amphoteric, that means it can exhibit acidic as well as basic nature. V2O4 dissolved in acid to give VO2 plus salt. Similarly, V2O5 reacts with the alkalis as well as acids to give VO4 3- and VO4 plus respectively. So that means it represents its amphoteric nature. It can react with acidic as well as basic compounds. The well characterized CRO is basic, but Cr2O7 is amphoteric. Now let's talk about some specific compounds. First is potassium dichromate K2Cr2O7. It is widely used in chemical reaction, and in our regular practicals we do use this compound in certain reactions. Potassium dichromate is very important chemical used in leather industry and as an oxidant for preparation of many azo compounds. Now azo compounds contains N double bond N bonds in between. That means it will be attached with certain other elements from both sides, and usually we have N double bond N in between. Dichromats are generally prepared from chromates, and which is in turn are obtained by the fusion of chromite or FeCr2O7. Now dichromate, that means Cr2O7, and chromate, that means CrO4. So it can be obtained by the fusion of chromite ore with sodium or potassium carbonate in free access of air. The reaction with sodium carbonate occurs as follows. So first of all, we have chromite ore and Na2CO3 in open air. So that means we have a good enough quantity of oxygen. Now when they react together, we get a chromate ion containing compound sodium chromate and oxides of Fe and carbon dioxide. Now this compound Na2CrO4 will be used for our next step reaction. Yellow solution of sodium chromate is filtered and acidified with sulfuric acid to give solution from which orange sodium dichromate Na2Cr2O7 2H2O can be crystallized. So when we use Na2Cr2O7 in acidic medium, you will get Na2Cr2O7 2Na plus and H2O. So that means chromate to dichromate. Sodium dichromate is more soluble than the potassium dichromate. The latter is therefore prepared by the treating the solution of sodium dichromate with potassium chloride. That means we can exchange Na and K, and that's why you will get potassium dichromate, and as mentioned it is comparatively less soluble, so we can filter it out. Orange crystals of potassium dichromate crystallizes out. The chromates and dichromates are interconvertible in aqueous solution depending upon the pH of the solution. So as we already saw in previous reaction, when we have acidic medium, we can convert chromate into dichromate, CrO4 into Cr2O7. So similarly, we can reverse that reaction. That means by changing the pH, we can interconvert chromates and dichromates into each other. The oxidation state of chromium in chromate and dichromate is same. Now let's check that point. So structure of chromate and dichromates are mentioned here. So let's check the attachment with the chromium and let's try to find oxidation state. So first in chromate ion we have 1 chromium and 4 oxygens, and overall charge is -2. So that means it is CrO4 2 minus. Now total 4 oxygens combinedly will give us -8. That means for chromium it should be +6. That's why overall charge is +2. So that means chromium is in +6 oxidation state. Now let's check for second dichromate ion. So we have 2 chromiums and total 3 plus 3 plus 1, 7 oxygens. So it is Cr2O7, and overall it has -2 charge. So total 7 oxygens will give us -14 charge, and we have 2 chromiums combinedly which gives +12 charge. That's why overall charge is -2. So 2 chromium gives +12. That means single chromium will be in +6 oxidation state, same as previous chromate ion. So structure of both are as mentioned here, and the chromate ion is tetrahedral, whereas the dichromate ion consists of 2 tetrahedra sharing one corner with CrOCr bond angle of 126 degrees. Sodium and potassium dichromates are strong oxidizing agents. The sodium salt has greater solubility in water and is extensively used as an oxidizing agent in organic chemistry. Potassium dichromate is used as a primary standard in volumetric analysis. That means in volumetric titration, it is a standard compound from which we can compare the other compounds. In acidic solution, its oxidizing reaction action can be represented as follows. So Cr2O7 2 minus with acidic medium, that means 14H plus and 6 electrons, it gives us Cr3 plus 7H2O. In this reaction, oxidation state of chromium is decreasing and acid is being neutralized, and cell potential for this or standard potential for this reaction is 1.33 volt. So that means it is spontaneous reaction. Thus, acidified potassium dichromate will oxidize iodides to iodine and sulfides into sulfur, tin 2 plus into tin 4 plus, and iron 2 salts into iron 3 salts. The half reactions are noted as below. So as we can see in all of this example, oxidation state of respective compounds are increasing. For iodides, it has -1 oxidation state to iodine, that means 0 oxidation state. Sulfides, again it is negative, and sulfur, that means neutral. And remaining are mentioned 2 to 4, 2 to 3. So 6I minus gives 3I2 and it releases 6 electrons. For H2S, it is -2 oxidation state of sulfur, which gives us sulfur, which is 0 oxidation state. Tin 2 to tin 4, Fe2 to Fe3. So all of them are oxidation reaction with Cr2O7. The full ionic equation may be obtained by adding the half reaction of potassium dichromate to half reaction of reducing agent, as for example reaction of Fe with chromium. So Cr2O7 2 minus with 14H plus electrons will be consumed from both sides, or it will be used on both sides, so it will be cancel out 6 Fe2 plus, 2 Cr3 plus, 6 Fe3 plus, and 7 H2O. So that means it is combination of two reactions, this and this. So as you can see, we have reactants in first reaction and reactant of second reaction. So Cr2O7 2 plus plus 14H plus from the first reaction and 6 Fe2 plus from second reaction. Electrons will be present on both sides. That means in first reaction we have electrons on reactant side, in second reaction we have on product side, so it will be cancel out. Now products on first reaction 2Cr3 plus and 7H2O, and product of second reaction 6Fe3 plus. So this is overall reaction or combination of two half reactions. Similarly, you can generate the reaction for remaining three reactions. That means Cr2O7 2 minus plus 14H plus 6I minus will give us Cr2 2Cr3 plus 7H2O and 3I2. Electrons on both sides will be cancelled out, and similarly you can do for remaining two reactions as well. Next is potassium permanganate KMnO4. So potassium permanganate is prepared by fusion of MnO2 with an alkali metal hydroxide and an oxidizing agent like KNO3. This produces the dark green K2MnO4, which disproportionates in a neutral and or acidic solution to give permanganate. So first MnO2 with KOH and O2 gives K2MnO4 H2O, and this K2MnO4 we will use the ion of K2MnO4, that means MnO4 2 minus with H plus gives MnO4 minus MnO2 and H2O. So it is disproportionation reaction. So how can we identify disproportionation reaction? First you have to find the oxidation state of our reactant, and then as we can see we have two different products having same element, and now try to find the oxidation states of both of that products. So first of all we have MnO4 2 minus. So oxygen will give us -8. Total we have 4 oxygen, that means -8 charge, and overall charge is -2. That means Mn should be in +6 oxidation state. So before reaction we have +6 oxidation state. Now in MnO4 minus we have total 4 oxygens again, so that means it has -8 oxidation state, but overall charge is -1, so that means Mn should be in +7 oxidation state. So here we have +7 oxidation state, so more than reactant. Next MnO2. So total 2 oxygens will give us -4, and that means Mn should be in +4 because it is neutral. So we have two different products having higher oxidation state than the reactant and lower oxidation state than the reactant. So that's why it is disproportionation reaction. Commercially, it is prepared by the alkaline oxidative fusion of MnO2 followed by the electrolytic oxidation of manganate 6. So as we can see, MnO2 fused with KOH and oxidized with air or KNO3. which gives manganate ion MnO4 2-, in which Mn is in +6 oxidation state. Now this manganate ion will undergo electrolytic oxidation in alkaline solution, which gives us permanganate ion, in which Mn is in its maximum possible oxidation state +7. In laboratory, that means when you will try to do this reaction, a manganese 2 ion salt is oxidized by peroxo disulfate to permanganate Mn2 plus with S2OH 2- in presence of water. It will give us MnO4- and 10SO4 2- and 16H plus. Now note here, we need some strong reactions to convert or to produce MnO4-, because in this case Mn is in its maximum oxidation state +7. So you need to remove total 7 electrons from neutral atom of manganese. So removal of 7 electron is very difficult. As we know, as we remove the electron, ionization enthalpies increases sequentially. That means first ionization enthalpy will be less than second, second will be less than third, and third will be less than fourth, and so on. So that means as we reach to 7th ionization enthalpy, we need to put very high amount of energy, or we need to use very strong compounds to react with. That's why we need some stronger reactions. Potassium permanganate forms dark purple almost black crystals which are isostructural with those of KClO4. The salt is not very soluble in water, 6.4 gram per 100 grams of water at normal temperature. But when we heat it, it decomposes at 530 Kelvin. So KMnO4 will decompose into K2MnO4, MnO2 and oxygen. So this reaction is actually used in primary standard by you. In production of gases, when you try to produce oxygen gas, we can use KMnO4. It is comparatively less hazardous reaction. That's why, to demonstrate practical to the student, this compound is being used. When we heat KMnO4, as we can see, oxygen gas will liberate. So production of oxygen can be demonstrated with KMnO4. It has two physical properties of considerable interest: its intense color and it is diamagnetism, along with the temperature dependent weak paramagnetism. So as mentioned, it is intense color. So that means very small amount of potassium permanganate can give us very very dark and or intense colored compounds or solutions. So when you add a very small amount in water, you will notice color of water is very intense, even in very small amount. And similarly, normally it is diamagnetic, but with the changing temperature it shows weak paramagnetism. These can be explained by the use of molecular orbital theory, which is beyond the present scope. So it is very complex because MO theory of this complex molecule is very hard, and it has very complex explanations. That's why we are not going to discuss in this unit. The manganate and permanganate ions are tetrahedral. The pi bondings takes place by overlapping of p orbital of oxygen with d orbitals of manganese. The green manganate is paramagnetic because of one unpaired electron, but permanganate is diamagnetic due to the absence of unpaired electron. Acidified permanganate solution oxidizes oxalate to carbon dioxide, iron 2 to iron 3, nitrites to nitrates, and iodides to free iodine. The half reactions of reactants are as we can see. And first of all, these are the structures of both KMnO4 2- and KMnO4-. That means manganate and permanganate ions. Now naming scheme, as we can see here, name of this ion is mentioned as manganate, and the second one is permanganate. So at suffix is being used in first, and per prefix and ate suffix is used for this second compound. So we can understand it using the example of chlorines. So oxo anions of chlorines has too many examples. That means ClO. So different examples of this compound are as shown. We have ClO minus, Cl2O minus, ClO3 minus and ClO4 minus. Now let's try to find oxidation states of chlorine in each example. So first of all, in first example, chlorine will be in +1 oxidation state because oxygen shows -2 oxidation state. So +1 -2 overall -1. Second, chlorine shows +3 because of 2 oxygen we have total -4 charge, +3 -4 -1. Similarly, we have +5 and +7 in last example. So let me show you the overall calculation for last example so you can calculate the remaining if you have any confusion. So we have 1 chlorine and total 4 oxygens and the overall charge is -1. So we do not know the charge of chlorine. So right now we will put as a Cl. Now total 4 oxygens will give us -8 charge and that's why overall it is -1. So 1 Cl is equal to -1 plus 8. This 8 will shift on other side. That's why it is +7. So 1 chlorine shows +7 state in this example. So when we have multiple different oxidation state, then lowest oxidation state will use hypo prefix and ite, ite suffix. That means this compound will be hypochlorite. Then next one which has higher oxidation state than the previous, it uses just ite prefix suffix, sorry. So it is chlorite. Then we have next with ate suffix, that means it is chlorate. And then higher oxidation state will use, highest oxidation state in this case will use per, per prefix and ate suffix. So that means it will be per chlorite, just like potassium per manganate. It uses at suffix. In this case we have per at prefix and suffixes. And suppose you have even more higher oxidation state, then in that case we will use hyper at, that means hyperchlorate for, let's say, for this example. So these compounds will be named as hypochlorite, chlorite, chlorate and per chlorate according to this nomenclature. And if suppose it has, actually do not have any higher oxidation state, but still if it is it has any higher oxidation state, then it will be called hyperchlorate. Now let's quickly observe the reaction. So we have 5 COO minus, that means oxalate ions, which gives us 10 carbon dioxides and it releases 10 electrons. Fe2 plus will convert in it Fe3 plus, NO2 minus into NO3 minus and I minus into I2. Just like before, the full reaction can be written by the adding half reaction of KMnO4 to the half reaction of the reducing agents, balancing whatever the necessary. If we represent the reduction of permanganate to manganate, manganese dioxide and manganese to salt by half reaction. So as you can see here we have MnO4 which gains electron and converts into MnO4 minus. Then MnO4 minus into acidic medium gives MnO2 and MnO4 minus in higher acidic state it gives Mn2 plus. So depending on the surrounding atmosphere or other reactants, it gives different type of products. We can very well see that the hydrogen ion concentration of the solution plays an important part in the influencing the reaction, although many reactions can be understood by consideration of redox potential. Kinetics of the reaction is also an important factor. Permanganate at 1 molar concentration of H plus should oxidize water, but in practice the reduction is extremely slow unless either manganese 2 ions are present or the temperature is raised. A few important oxidation reaction of KMnO4 are given below. So first reaction for iodine, as just discussed in previous example, it is the combination of two half reactions. Second, for Fe, again combination of two half reaction. Fe plus 2 will oxidize in Fe plus 3. Then next, again the reaction already discussed, oxalate ion will convert into carbon dioxide. Then we have a new reaction, H2S into S plus. So half reaction is mentioned and overall reaction is again mentioned. So how can you find the overall reaction? Let's discuss this with the given example of H2S. For that, you need to find the oxidation state change for both of the main reactant, that means MnO4 and sulfur. In case of sulfur, initially sulfur has -2 oxidation state. Okay, so it is already mentioned here. And for Mn, oxidation state here is +7. So it will convert into +7 to +2. So total number of electrons is equal to 5. Total change is equal to 5 electrons. 5 electrons are actually removed. So that means we need same number of electrons for second reagent. So conversion of sulfur into sulfate ion into sulfur, it has total gain of 2 electrons. So that means we need to multiply sulfur with 5 and we need to multiply Mn with 2. So that's why we have 2 MnO4 minus and we have 5 sulfurs. So overall 10 electron transfer will takes place. Next, SO3 to SO4 and last NO2 to NO3. Now next, in neutral or faintly alkaline solution. Now same compound can give different type of reactions in different type of medium. So as we can see in this case, here we have MnO4 plus H2O plus I minus, which gives MnO2 plus 2OH minus with IO3 minus. So iodide to iodate. So as we can see, here we have IO3 minus, which is mentioned as iodate. Just like chlorate, it is iodate. Thiosulfate is oxidized by almost quantitatively to sulfate. So MnO4 plus S2O3, that 2 minus, that means it is thiosulfate, which gives us SO4 2 minus into sulfate. And last reaction, manganese salt is oxidized to MnO2 and the presence of zinc sulfate or zinc oxide catalyzes the oxidation. That means it will increase the speed of reaction. But it is catalyst, so no need to mention it in overall reaction. So MnO4 minus with 3Mn2 plus, overall it will convert into MnO2 and 4H plus.